So the idea is to determine how much fluid pressure there would be and to design your holding tank with enough strength to withstand the pressure. How many of you ever scuba dived? Anybody? Have you heard about like people who dive down and the fluid pressure can cause a person's eardrums to burst if you don't go down with the appropriate gear, because you have to keep the pressures equalized. All right. It's all about fluid. All right. So we want to talk about the force that it's exerted by a fluid. So F is going to be the force. All right. First, you have to know the density of the fluid. It's a constant. Every fluid has its own density. So you could plan something to hold the density of water, but if instead you fill it with molasses, molasses has a different density than water does. And so now maybe the thing that you originally designed to hold water can't hold the molasses because molasses is more dense, or oil or any other liquid. So first you have to know that. That's a constant, right? Because it's a constant, it's on the outside of your integral. On the inside of your integral, you have to multiply two things. The cross-sectional width of the fluid itself. Okay, so all the way across the fluid, and how would you express that? And we need to know the depth of the fluid. Not only is the fluid pressing out or necessarily pressing in a vertical direction, but what else is pulling on the fluid? Gravity. Okay, so all of this is going to be in terms of y, and so this will be dy. And our bounds are going to be c to d because we're doing everything in terms of y. Okay, how do you determine the cross-sectional width? So that's the ultimate formula, and then it's just setting it up. The width is going to be x, but it's going to be expressed in terms of y. So x equals something. So if you're given an equation, you have to convert it into y terms. So width is always x. It's a horizontal width, cross-sectional, but it's expressed in y terms. The depth, because gravity is pulling down, you start at the top of your fluid, and then you subtract the height, which is basically the top minus y, because y is representing the height. And so it becomes then a plug and chug. You plug in the density of the fluid as your constant. Your bounds would be the height of the object. The cross-sectional width is always x, but it's expressed in terms of y. And the depth will be the top of the fluid, and then minus the height, which is going to be y itself. The height of the, how high the fluid is.
So when you say top is like the container?
Okay, so it depends. Most of these we're going to start with it being full. All right. If it's just sitting there, then the top will just be the top of the fluid. Okay. We're going to do another one on work. That's the next the formula that's going to come on work for this, and there it'll be to the top of the container, even if the top of the fluid doesn't reach to the top of the container. Well, because y is changing as we go. Okay? Yes, yes, the original height. Okay, but as it's leaking. Okay, right. As I mean, this is changing, right? It's almost like think of it like stacked cylinders. So like here, this lowest level of fluid, okay, that has a different fluid force because it's closer to the ground, as opposed to the level of fluid right there, like the super thin level of fluid, that has a different fluid force because it's higher off the ground. And so not only is this, but it's building on top of what's on top of it. And then as you move up, this level of fluid also is contributing to the fluid force. So the higher up you go, so if you're sitting down here, not only do you have your own fluid force, but you have all the fluid force of everything above you. Okay, which one has the least amount of fluid force? The one that's sitting on the very top. So that's why the top minus y would be a very small number once you're near the top. It still has the fluid force of the cross section, but it doesn't have all the fluid on top of it pulling it down. But when you're down here, or even in the middle, that's why the deeper you go, the more force you have. Yeah.
So is y a function?
Y will be a function. No, y will be just a variable. X is the function. Yeah, x is the function. Yes?
Can you explain the cross section of?
Yeah, let me draw one for you.
Okay.
Okay? We just got to go across. Okay, we have a triangular trough. I love the word trough. Looks awesome. Okay, this is something like an animal would drink out of. Okay, so it's a triangle here, but then it goes back like this. Okay, and that's filled with water or fluid. Let's fill it with water. All right, the top is 8 feet, and the depth is 6 feet. All right, so this is huge. This is like at a big farm, and you've got all these animals coming to drink out of this big trough. So if we can imagine, we've got 8 going across here, and then 6 is the height. All right, water fills the trough. The water has a density of 62.4 pounds per, oops, I can't spell, pounds per cubic foot. You will always be given the density. You don't have to memorize the density of the different liquids. All right, so water fills the trough to within 1 foot of the top. So it's not totally full. Okay, so if I were to put my water on there, oops, my water would be like up to about right there. Okay, that's the water level. All right, we want to figure out how much fluid pressure, how much force is being exerted on the sides of this trough. You're going to want to superimpose an origin on here so that we can come up with an expression of an equation, because there's no necessarily equation. We're going to have to make one. So I would always recommend putting your origin at the bottom. That's always going to be the easiest. And so if we put our origin right here and we call that 0, 0. So if we do that, what would be the coordinates in space of this upper corner right there? Okay, because 0, 0 is in the center. And so then what would be the coordinates of this one over here? -4, 6. All right, if those are the corners, if we superimpose and we decide, you could put your origin wherever you want. If you wanted to put the origin on one of the upper corners, but I usually feel like it's easiest to put it in the bottom in the middle. What is the equation that connects these 2 points? From 0, 0 to 4, 6. Say that again? Okay, 3 over 2 x, right? That's the equation that expresses that side. And what about the other side? Y equals negative 3 over 2x. All right, so now what's the cross-sectional area going across from one side of the edge to the other side of the edge? Okay, not quite. All right, going across from here to here, the width will be 2x. Right, because x to one side and negative x to the other, and so 2x. But I need to express that cross-sectional width in terms of y instead of in terms of x. So is that where you were going? Not
No,
okay. That direction is x, and that direction is negative x. Because we put the origin at the bottom. Okay, we put the origin at the bottom. But we want to express that in terms of y, in order for, because I'm integrating in terms of y. So we know that, you guys set up, y equals 3 over 2x. So what would x equal? 2/3 y. So if x is 2/3 y, then this would be 2 times 2/3 y. In other words, 4/3 y. That is our width, our cross-sectional width at any given point for this fluid. All right, so let's see if we can set up an integral to find the fluid force. F equals, all right, the density 62.4 goes out in front. What are my bounds? 0 to 5, because it's only filled to within 1 foot of the top. Mm-hmm. That's just an English expression of that it's 1 foot, 1 less. Yes, as opposed to exceeding it by it's 1 less. All right, then we need the cross-sectional width, which we just came up with, is 4/3 y. And then we need the top of the fluid, which we decided was what? 5 minus the variable y, the height, dy. The setup is, once you have the setup, then you can just use your calculator to integrate that. The fluid force, yeah, fluid pressure, force, same thing. Okay, when it's when we're talking about liquids, you call it a fluid pressure, but that's what force is when talking about liquids. All right, so that works out to be, you can use your calculator, 433 1/3 pounds of force. Yes, sir.
I don't really get the part when we are converting x to y in terms of
Okay.
so this is a triangle with 2 equal sides. So
Mhm.
if, so like one side is a curve, the other side is a line. That how to find.
Okay, no problem. One side is a curve, the other side is a line. Okay? All right, let's make it easy. Let's say that that's 2x, and let's say that this is x squared. Okay? If you want to find the across for this. All right? If that's x1, then this would be 2 times x1. Yes? If this is x2, then this would be x2 squared. Okay? What is the width of this?
2x1 minus x2 squared.
No, the 2x1 is a height. The width,
Oh,
okay,
x1 minus
x1 minus x2.
Oh.
That's it. That's the width. Okay, now if we want to express this in terms of y, the other way around, then we say x equals 1/2 y, or x equals the negative square root of y, because it's the negative side of the parabola.
Oh.
Okay?
So technically, for
So then it would be 1/2 y minus the negative square root of y. That is the cross-sectional width expressed in terms of y instead of in terms of x.
oh,
Okay?
so in the example, we can also do it like we convert two equations and
Yeah,
to
yeah.
x.
In our example, it worked too. Okay, we had this. All right, this is x1, and this was 3/2 of x1. This is negative x1 because it's symmetrical, and that was negative 3/2 of negative, I guess it's going to end up being positive 1, like that. Okay, the width is still x1 minus negative x1, so 2x1, because these are equal. x1, because ours is symmetrical, we don't have any different, they're not different. Okay, if we convert it and we say we want it in terms of y, then we know that x on this side, x1, is equal to 2/3 of y. On this side, x1 is equal to negative 2/3 of y. So then we subtract 2/3 of y minus negative 2/3 of y. We still get 4/3 of y, which is the same thing we got last time. Okay? All right, good job. Oh. Okay, yes, ma'am.
How did you get that answer? Like, you have to like do conversions with like your integral. Like,
Okay. Oops. This is the last thing. All right, here's the math on the molasses example. All right, a cylindrical tank. All right, the tank, then these are the actual dimensions, 90 feet high and 90 feet across, which means a radius of 45 feet. The molasses density is more than water. The molasses density is 100 pounds per cubic foot. 100 pounds per cubic foot. All right, we want the cross section of this. Find the force on the external wall here. All right, so what shape is a cross section of this?
Circle.
Okay, a circle. All right, so we want, but the whole circle is not touching the external wall. Okay, only the circumference of it is touching the external wall. So I want the edges that are touching this thing. That's a circle. Last time we had a triangle and we were only doing a cross section of this. This has a cross sectional area. Okay, so our force will be 100 times the integral. Okay, we're going to assume this thing is full. So my bounds will be what? Okay, I want the cross section, and I want the edges of the cross section that are touching the external wall. So that's the circumference. So 2 pi times what? 45, right? 2 pi r is circumference. All right, then I want the top.
If it was what if
Something has to be in
it's
terms of
triangular
y.
top, shouldn't it be the whole rectangle?
But this is constant, right? This is not changing, not like the triangle. The triangle had a changing cross section. As I went across, the triangle was always getting wider and wider and wider and wider. This one, no matter how I slice it, it's still going to be a constant.
Dude, why wouldn't our cross section do
But
the
it
example
would
like
still touch the
rectangles?
rectangular part of the trough.
The rectangular part of the trough.
I think you're taking like a different direction of cross section, like you're slicing.
Here, we're still slicing. This is slice, 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 slice,
The
slice.
water also touches the plane side.
If you take those, then those are like.
My slices here are circular.
What does it mean by like
That's
in the
it,
width?
yeah.
I don't get it.
It's like if you on the top of the
Okay, how can I?
We want to make it like the whole thing, like the triangle. And it would kind of be like rectangle with like these.
We were just doing on this front edge.
Why?
Because that was the only part of the question that we wanted to know. If we wanted to know the whole thing, you'd got to multiply by it. You'd have to know how long the trough was, which I didn't tell you.
What were we looking for in the first one?
The fluid force on the front panel, that front triangular. Yeah, just the front
You
panel.
didn't write that down.
Sorry. It's all right.
So what are we doing in the second?
The fluid force on the outer, the whole thing. And so then what is it? Yeah, yeah. And so then the top is 90 minus y dy. And then you've got it. Yes. I got 114 million. Yes, is that what you got? Okay, yes.
For the first problem, if we were trying to find the fluid force in the whole thing.
We would have to know how long the trough was, which I hadn't
then
told
we
you.
would do the perimeter.
Yes. Yes, because then the cross section would have the perimeter. Right.
Okay.
Right.
And, is 45 a radius or
45 is the radius.
a area?
Right, because the diameter is 90 and the sides were 90, so the radius is 45.
That was confusing.
I know, I'm sorry. It's the setup that's always so hard. Once you get it,
Yeah, it's just the fact that it was like, one was only finding the force on the top of
On the
it,
plane?
front, and we didn't talk about
okay,
that.
so let me put in my notes to make sure I specify that for next time. So, change it. You want,
Like in the first example, just say that it's
Yeah.
like the front panel, is what the force is.
okay, front panel. And so then this one, the external wall.
Oh,